Let's try to solve this problem here. So it has 3-point charges that are arranged along an x-axis. So you have charge Q1, which is negatively charged negative 4.50 nanocoulomb, and is located at x equals to 0.200 meter. So it's somewhere at the right of the origin because it's a positive 0.200 meter. Okay, charge 2, it's a positive charge, is 2.50 nanocoulomb, and it's located at x equals to negative 0.300 meter. So x equals to negative 0.300 meter is at the left of the origin because it's a negative x value. Okay, so you have a point charge is located at the origin. So there are 3 charge over here. I assume since this one is charge 1 that is located at x equals to 0.2, charge 2 is located at x equals to negative 0.3. So the third one will be charge Q3, and this charge Q3 is located at the origin. So let's draw out the situation here before we try to solve the problem. Okay, so let's try to draw an x-axis in dotted line, just to not confuse us with the forces and the field. So I'll label here as x equals 0. So over here, I believe the charge is a positive charge, which we call it as Q3. Okay, somewhere over here, you have your Q1, which is a negative charge. And the distance between the origin and this point okay, this distance here, it's 0.200 meter. Okay, at x equals to negative 0.3, which is somewhere slightly further away, probably here, you have a positive charge, which is Q2, which is equals to plus 2.50 nanocoulomb. And the distance between the position of Q2 and the origin should be 0.300 meter. Okay, I'm not putting a negative sign inside here because the negative is to indicate that it's at the left side of the origin. That's all. Okay, it's not indicating a negative negative value. I mean, yeah, it's just to indicate that it's at the left hand side of the origin. Okay, so this is the situation that we have. Let's look at what the question asked for. So what must the value of Q3 be? So this Q3, they don't tell us what's the value of the charge, right? So they ask what is the value of Q3 in order for the net force on this point charge to have a magnitude of 4.00 micro Newton. Okay, suddenly I never see micro Newton before. Okay, so they say what value does Q3 has to be in order for the net force acting on Q3 to be 4 micro Newton. Okay, so we know that Q3 is a positive charge, so let's try to determine what are the direction of forces acting by Q2 on Q3 and acting on Q1 by Q3. Let's try to determine the forces acting on Q3 first. So we are going to label the force factor here. Okay, so let's try to investigate Q1 and Q3. Q1 is a negative charge, Q3 is a positive charge, so they are opposite charges, so they should attract each other. So Q1 will attempt to pull Q3 towards Q1. So the direction of force should be pointing to the right. So this force here, it's called force acting by 3 on 1. Q1 is pulling, Q3 is being pulled. So the one pulling, it's Q1. The one being pulled is Q3. So by 3 on 1. Okay, it's exerted by 1 on 3. It's by 1 on 3, sorry. It's by 1 on 3 means that it's exerted by Q1 on Q3. Q1 is the one doing the pulling. Q3 is the one being pulled. Okay, so Q2 and Q3, what's their relationship? Q2 and Q3, they are both positive charge. Q2 is positively charged, Q3 is also positive charge. So since they are both positive charge, they will try to repel each other. So Q2 will try to push Q3 away. So away is in this direction. So you should expect that the force that is exerted by charge 2 on charge 3 to be pointing in the same direction as F13. Okay, Again, Q2 and Q3 are positively charged. They are like charges, they will repel each other. So Q3 will push Q2 in that direction, but that's not relevant for our discussion. What's relevant is that Q2 is pushing Q3 in this direction to repel it away. So F23 and F13 are in the same direction. Okay, and they tell that if you add these two up, the value or the net force must be equals to 4 micronewton. So that is our aim right now. If we add up F23 and F13 and the answer is 4 micronewton, then what will be Q3? Okay, so let's try to write it out in mathematical form. They tell us that the sum of force, okay, it's equals acting on Q3. So sum of force at 3 is equals to 4.00 micronewton. This is a situation that we know now. Okay, and since everything is happening in the x-axis, then there's nothing happening in the y-axis. So we can should we say sum of force acting on charge 3 x component, okay, there's no y component, just x component, is equals to F23 plus F13. Okay, and this should be equals to 4.00 times 10 to the power of -6. Okay, I hope you get the idea. We are doing the x component of force acting on Q3. It's like a free body diagram. You see in the x component, there's only F23 and F13, and they're both pointing in the same direction. So x component should add them both up. If they're in opposite direction, then you take one minus another one. But since they're in the same direction, pointing in the positive direction, you put positive for both of them. Okay, you label the direction using the sign. Okay, I can write in the positive over here as well. Okay, so now let's continue. Oops, substitute in the sign. So this is, I mean not sign, the equation, sub in the equation. Q2, Q3 over the distance between 2 and 3 square plus K, Q1, Q3 over R13 square. Okay, so something common over here, it's Q3. Q3 is common, so you can factorize it out. Then you can also factorize out the K. Then you are left with Q2 R23 square plus Q1 over R13 square. Okay, so that's the situation you have right now. So now we can substitute in all the value that we know. 4.00 times 10 to the power of -6. Q3 we don't know, we want to find. Okay, so K it's 9.0 times 10 to the power of 9. Okay, Q2 it's 2.50 times 10 to the power of -9. R23 it's 0.300 square. Okay, it's over here. The distance between 2 and 3 is 0.300 square. Okay, plus Q1 is negative, but since there's a modulus, we don't care about the sign. So 4.50 times 10 to the power -9. The distance between them is 0.200 square. Okay, the distance between here is over here. Between 3 and 1, the distance is 0.2. Okay, so now the only unknown you have is the modulus of Q3. So if you key into your calculator, you get the modulus of Q3 to be equals to 3.168 nanocoulomb. And since they already tell you in the question that it's a positive point charge, so you don't have to worry about the sign anymore. You know for sure that Q3 is equals to positive 3.168 nanocoulomb. Okay, before that, because here there's a modulus, you still don't know if you remove the modulus, it'll be positive or negative 3.168 nanocoulomb. But since the question already tells that it's a positive point charge, you can just put in the positive without thinking too much about it. Okay, so that's how you solve the first problem. Let's move on to the second problem. What is the direction of the net force acting on Q3? Well, you already can see that both of the forces are acting towards the right. So you can say for sure that the net force acting on Q3 will be pointing to the right. Okay. If you worry that there's no steps, right, you can say by referring to the electric force diagram, which is the diagram that I draw up here. Both F23 and F13 are pointing to the right. Okay, actually you don't need to explain all these things. I think it's quite straightforward. Everybody can see it's pointing to the right. Hence, the net force acting on 3, which is equals to F13 plus F23, should also be pointing to the right. Okay, nothing too complex. It's just looking at the diagram, try to explain the situation. Okay, last question. Where along the x-axis can Q3 be placed for the net force acting on it to be 0? So right now the net force acting on Q3 is 4.00 micronewton. But now they ask, if you want to shift this charge to somewhere else along the x-axis, where can you shift it to in order for the net force acting on it to be 0? Okay, to find the correct position to place the charge Q3 in order for the net force to be 0, you have to use some drawing actually. So I'm going to recreate the situation. You have a positive charge Q2, and you have a negative charge Q1. Okay, then I draw a line, dotted line representing the x-axis. So if you look over here, if you want to place your charge Q3 over here, let's do a hypothetical case. Let's say if you place your charge Q3 over here, you see that both of the forces are pointing to the right. F13 and F23 are both pointing to the right. So in this case, right, it's impossible for you to get 0 net force, because in order for the net force to be equal to 0, F13 and F23 will have to be both equal to 0, only the net force can be 0. But we know that's not the situation. So therefore, you should not expect Q3 to appear anywhere around here. Impossible to appear around here. Okay, because around here the diagram must be both pointing to the right. The force must be both pointing to the right. Okay, so let's try another situation. Let's say if we place our Q3 over here. If we place Q3 over here, then the force acted by Q2 on Q3, Q2 will repel Q3. Therefore, the force exerted by 2 on 3 will be pointing to the left. But Q3 and Q1, they are opposite signs, so they will attract. So Q3 will be pulled by Q1 to the right. So now this free body diagram here makes sense, because now as long as you are able to make F23 and F13 having the same magnitude, then they will cancel each other out because they are in opposite direction. As long as you can make F23 and F13 having the same magnitude, they will cancel out. Net force will be equal to 0. Okay, so that means by this place over here, it's possible. Okay, and from there you should also think that this place here should also be possible. Okay, if you can't believe it, you can try for yourself. Place a charge over there. Here there will be attraction by Q1, so this is F13, but there will be repulsion by charge 2, so F23 will be pointing in this direction. So this two regions here are possible. But which one is the correct region to place Q3? Well, for that you have to look at the charge over here. Q2 is 2.50 nanocoulomb, but Q1 is negative 4.50 nanocoulomb. Q1 has a stronger charge compared to Q2. So the force, right, for them to be equal, right, you have to place the charge far away from Q1 because Q1 is greater in electric charge. You need greater distance to lower down the force. But for Q2, since it's a smaller charge, you have to put it closer to Q2 in order to have a greater electric charge, a greater electric force. So to make F23 and F13 having the equal magnitude, you have to place Q3 nearer to Q2, further away from Q1. Again, nearer to Q2, further away from Q1. Because Q1 large charge, Q2 smaller charge. Okay, so this will be the correct position. This will be not the correct position. But because if you place it here, it's near Q1, but it's far from Q2. So the Q2 is already small already. If you still put R to be big, then it become even smaller, the force. So the logical one is to place it over here. Okay, so now I will clear out the diagram a little bit to do some labeling. Okay, so this is how I determine where should I put my charges along the x-axis. I put it at different position, then see which one makes sense. This is what I did just now. Okay, so this is the situation I have. So I'll label this. I know the distance between Q1 and Q2 is 0.500 meter. And the distance between Q2 and Q3 is just, let's just call it X because we don't know the value. So later we find the X, then we know where should we place our Q3. Okay, we know Q3 need to be placed here, But how far is it away from Q2 is what we want to find out. Okay, so over here, we want sum of force acting on charge 3 to be equals to 0 x component. So therefore, you know F23 is pointing to the left, F13 is pointing to the right. Therefore, you know that F23 should be equals to F13 in order for that to occur. Okay, so now you know K, Q2, Q3. Then what's the distance between Q2 and Q3? Between Q2 and Q3, the distance is x squared. Okay, on the other side, you have K, Q1, Q3, and the distance between them is 0.5 plus x. That's the distance between Q1 and Q3. 0.5 plus x. So 0.5 plus x squared. Okay, so when you reach this stage already, there are some stuff you can cross out. And cross out the K, you can cross out the Q3. So eventually you are left with Q2 over x squared, then equals to Q1 over 0.500 plus x squared. Okay, substitute Q2 is 2.50 times 10 to the power of -9. X squared is what we want to find, and is equals to Q1, which is 4.50. Again, don't put in the sign. Then 0.500 plus x squared. Okay, so now there's only one unknown, x over here. So if you use your calculator, you should be able to get your answer. X will be equals to 1.46 meter. Okay, and once you get the answer over here, you should not just stop, because this is just filling in the value over here, 1.46 meter. So you still have to describe it correctly. Okay, I have no space, I write it over here. Q3 should be position at 1.46 meter to the left of Q2. Okay, so if you place Q3 at 1.46 meter to the left of Q2, then at that position, Q3 will have equal magnitude of force acting to the left and to the right. Therefore, the net force acting on Q3 will be equal to 0. Okay, so that is how you solve this kind of problem here. Again, you have to deduce which region will the charge be placed. Only from there you start to work out the forces, the direction of the forces. Only you start to work out all this calculation over here. Okay, so that's all for this question.